Here in the lab on the chip
field, the primary goal is to recreate human complex biological systems on a single chip to investigate the reactions to drugs, contaminants, and wounds as well as course of disease. Cell proliferation and cell migration involving the movement of cells in response to biological signals and environmental cues play a vital role in a variety of key physiological processes, including immune cells recruitment, wound healing, and tissue repair, as well as embryonic morphogenesis. Cell proliferation and cell migration is frequently tested using so-called wound healing assays, which are based on the inherent ability of tissue cells to move into adjacent cell-free areas, thus providing important information on cell viability, cellular interaction, and cell motility. In addition, such assays are applied in cancer research to test the aggressiveness of cancer cells to form metastasis and allowed to test for drugs that inhibit metastasis and/or cancer growth. Despite recent achievements, it has been recognized that only a better understanding of the complex, dynamic processes that govern cell migration will foster the development of novel therapeutic strategies. In other words, to accelerate discovery of therapeutics affecting cell motility, wound healing assays need to be performed in 3D microenvironments that mimic structures and architecture of native tissue. To overcome the limitations of current migration and wound healing assays, we have developed an automated miniaturized lab-on-a-chip system that is capable of reproducibly inducing cell-free areas, wounds, in 2D and 3D cell culture systems. Mechanical wounding of confluent cell layers and 3D artificial microtissues is accomplished by integrating pneumatically driven actuators that A. allow the generation of highly reproducible injuries, less than 4% RSD, B. enable repeated wounding of a single wound area, and C. regulate applied compression forces. Performance analysis demonstrated that our computer-controlled organ-on-a-chip technology can automatically perform cell culture handling, wounding protocols, and monitoring of migration capacity in the absence and presence of bioactive compounds. Overall, monitoring dynamic cell migration and invasion processes using an automated, miniaturized and integrated microfluidic 2D and 3D cell culture system will offer an unprecedented ability to identify novel targets for intervention in critical physiologic and pathologic phenomena. The use of physiologically relevant 3D cell-based assays earlier in the testing paradigm further allows for more effective identification of lead compounds and recognition of undesirable effects sooner in the drug discovery screening process.